All right, today we're going to start talking about proportions in solution mixtures. Now, our goal, our objective is to actually be able to calculate some of these things. You are pretty familiar with something called a percent, okay? With something called a percent, because that is dealing with the 100. So how many in 100? So if we would say, you got 25%, you would know that that would be 25 out of 100, correct? But what if I'd ask you something like a part per million, a part per billion, a part per trillion? Those are not as recognizable to us as a part per 100. So, we're going to discuss those different types of concentrations. So, if we're expressing concentrations with percentages, we're talking about the amount of solute divided by the amount of the solution, and then we multiply by the representative quantity. So if we were putting it into a percentage, you would take the amount of solute, the amount of solution, and that representative quantity would be 100, because that's how you do percent. So 10 to the second would be parts per 100. Ten to the sixth would be parts per million. 10 to the ninth would be parts per billion. And 10 to the 12th would be parts per trillion. Now, if you see right here, here is how we label parts per million. ppm, ppb, parts per billion, ppt, parts per trillion. You're usually going to see them in lowercase letters too, folks. Usually they'll be in lowercase. So if we were going to put something into a part per million, we would take the amount of solute, divide that by the amount of solution, and then multiply it by 10 to the 6 to put it in parts per million. One part per million is equal to 1 part of a substance in 1 million parts of a water solution. So 1 million water solution parts, 1 part. Now, I've got this little jug up here, okay? I've got this little jug up here. Now, I definitely wouldn't want this job, but there are 1 million little balls in here, so to speak, and this is signifying 1 part per million, because of the million little balls in here, there's one that is not yellow, it is black. Okay? So, sometimes we just, I don't spend a lot of time in life with this, but can you see, Max, Ethan, the one black little sphere in there? It's in there. I'm telling you, it's in there, but we mix it up. Okay? And it's easier on this one because there are only the yellow and the one black. Okay? I wouldn't want to be the guy that had to count out 1 million little yellow spheres either. Okay? That seems like a bad job. But I'm sure that they have some kind of computer stuff to do it. So, sometime if you got a second, see if you can find that. Now, this one's a little bit harder because it has mixed in blue, which is the background particles, orange, red, white, pink, green, and black. Okay? 10 parts per million green. So there are 10 little green balls in here, and they are tough, and I'm telling you, it's tough to find. Okay? Green ones, it's even tougher to find the black one because there's only a single 1 part per million in here. Okay? So sometimes check those out to see if you can find them. Yeah. Yeah, I don't think so. Okay? I don't think so. I don't think that would be very much fun. 1 part per million, just to give you a perspective. 1 part per million is approximately 1 second in 11.6 days. So it is a very, very small number. 1 part per million is. One part per billion. The concept of part per billion. Once again, 1 part of a substance in 1 billion parts of water. 1 part in 1 billion parts of water. 1 billion, 1 part per billion is approximately equal to 1 second in 31.7 years. So 1 part of the substance in 1 billion parts of water. Now, you can probably think of what's coming next, the concept of parts per trillion. 1 ppt, 1 part per trillion, is 1 part of a substance in 1 trillion parts of a water solution. The bottom number, there's the 1 part, there's the 1 trillion. And 1 part per trillion is approximately 1.6 days out of the present age of the Earth, which is approximately 4.5 billion years. I always love those comparisons because, I don't think we have any concept of a billion. Okay? It'd be nice to have a billion. I'd take a billion pennies. I don't know how much that would be, but I'd take it. Okay? But 1 day out of approximately 4.5 billion years. So, what does this whole concept of these things mean? Well, we've got to be able to calculate these when we need these. So there are certain steps we have to take. And those steps involve, first of all, converting all volumes to milliliters and all masses to grams. Step 1 says to convert all masses to milliliters and all masses to grams. Step 2 is to divide the amount of the solute by the amount of solution. And it says the units must match the dimensions. Okay, the units must match the dimensions. I just gave you a little half sheet of a paper. Okay? Let me call up that little half sheet of a paper. I guess I can let you, whoa. I'll let you copy this first. Okay? Let me freeze this up here while you're copying it, and I'll see if I can find that. No, I know I can find it. It's just finding it. So you have this chart here. Well, you can wait here in a second. We'll get it. You have this chart here. It's pretty hard to read up here. I understand that. Okay, you have it right in front of you. So as we have that chart, I'm going to try to make it bigger here. Okay, they show you specific amounts, specific units that you can use for these things. And this is going to come in more handy a little bit later on. Okay? But we even got some conversions. You know how to do the conversions. We did metric conversions way back in the beginning of the year with these stuffs. You might want to review those. Okay? But now we have to take the amount of the solute, divide it by the amount of the solution, and then finally, we have to multiply by what we're dealing with. What do we want it in? Do we want it in parts per trillion? Do we want it in parts per million? Parts per billion? Parts per 100? Okay? So, we need to have that representative quantity, as we were talking about earlier on, which is either 10 to the second, 10 to the 6th, 10 to the 9th, or 10 to the 12th, depending on what we are converting to, what our label is going to be. So here's the first practice problem. Go ahead and write it down, and then we will calculate it. The problem states, find the percent concentration of a solution in which 6.8 grams of sodium chloride has been dissolved, making a solution with a volume of 85 milliliters. So what we need to do is, okay, we make sure that we have milliliters and grams, which I already have. If not, I would have to convert those to either milliliters or grams. But I have them, so my first step's already done. My second step is to take the amount of the solute, 6.8 grams, of NaCl and divide it by the amount of the solution. Now, what am I trying to put this in? A percentage, which is actually a part per 100. So now I'm going to multiply this by 10 to the second. Well, 10 to the second is actually 100. We've probably done a percent calculation multiple times throughout our learning career. So I take the 6.8, divide it by 85, multiply that number by 100, and it looks to me like I have two significant digits. So I am going to get 8. Does that sound right? Okay. %, correct? Now that's not tough, is it? Now, let's come up with my second example. Go ahead and copy that down. It is a part per million example. Find the concentration in parts per million of a solution in which 0.0059 grams of sodium chloride has been dissolved, making a solution with a volume of 750 milliliters. Once again, step 1, convert all volumes to milliliters and all masses to grams. We've already done that. So step 2 is divide the amount of solute with the amount of solution. So my amount of solute is 0.0059 grams. The amount of solution is 750 milliliters. Now, here's the part. We need to multiply it by the part per million number, which is 10 to the 6th, correct? So when I do that, divide 0.0059 by 750, and then multiply that value by 10 to the 6, and I get, how many sig figs? 1, 2, 1, 2, 7.9, and my label is going to be ppm. 7.9 parts per million. Here's a part per billion. Go ahead and copy that down. And notice that our values for our solute are getting very, very, very small. Now, once again, the amount of solute, 9.6 times 10 to the negative 6. Now, here's a point. Do we have grams per milliliter? I do not. So what do I need to do? I need to convert my liters to milliliters. Well, how many milliliters is 2 liters? How do we move it? Which way? We jump 3 to the right. So it is 2,000 milliliters. So I take 9.6 times 10 to the negative 6, and I divide that by 2,000. And what am I multiplying this by then? And I'm multiplying it by 10 to the 9th, correct? Because I'm doing parts per billion. And when I do so and multiply that by 10 to the 9th, I get a value of 4.8 parts per billion. Yeah. Right, but look at this number right here, 2.0. Yeah, the 2.0. I mean, if you want, I could put a bar there. Probably should, because that 2.0 is still, even when I convert it into milliliters, okay? I go back to my original numbers with the sig figs. Okay? Now, I am going to do one more, and I don't think you need to write this whole problem down, but let's just go ahead and read it and we'll work it. Okay? It has a lot of misinformation in it that you don't need. It says that an Olympic-sized swimming pool is 50 meters long, 25 meters wide, 2 meters deep. It holds 660,000 U.S. gallons, or 2,500,000 liters of water. It has 8 racelings that are 2.5 meters wide, with an empty lane of 2.5 meters width along each side. Okay, now it's telling you, basically what we are doing here is we are putting 1 gram of salt into a pool of that size of water. Now that's a pretty lot of water and a very little amount of salt, isn't it? Okay, so if we are calculating our parts per trillion, well, what is our amount of salt? We've got 1.0 grams of salt that we put in there, right? We need to have the volume of our solution in milliliters, right? Here is the volume of water of that pool in liters. Can I convert that into milliliters? Yes, I can. So I'm moving it 3 places to the right. So basically, I'm just adding 3 more zeros. Now, to make it into a part per trillion, I need to multiply by what? 10 to the 12th. So that is going to give me when I come up with the value, and I'm putting that bar above the second zero right there because I have 2 sig figs, or another way I could have done it. Whoa, whoa, whoa. Or I could have done it 4.0 times 10 to the 2 parts per trillion.